So in this video, we're going to think about multiple echelons in a supply chain and determining the network not just for one echelon, but two echelons. So in this example, we're going to think about locating both factories and warehouses. And so we're going to figure out where both the yellow boxes and the triangles are. And then once we have them located, we need to allocate the resources from suppliers to factories, factories to warehouses, warehouses to customers. And so in everything else we did before, we really had one echelon of decisions. We made one type of facility, and then on both sides we had as fixed or input parameters. Here we have two decision epochs or decision echelons. In this example, could be factories or warehouses. It could be other things in your supply chain. And so what does that mean? Before we get into the meat of the model, I think it's useful to think about why would we do that? What's the benefit of this? Is this good, bad? Does this make it more complicated, easier? And so here's kind of a knowledge testing intuition, okay? So consider a network design problem where the goal is to minimize the cost of producing products at factories, as well as the cost associated with transport between factories and distribution centers, and transport between distribution centers and retail locations. Model 1 considers the location of factories as fixed. So in other words, we don't get to determine where should factories be located, and determines which distribution centers are open. So we get to determine locations of distribution centers, but the factory locations are fixed. Model 2 considers that we get to decide both the factories and the location of distribution centers. Okay? So what does that mean in terms of this problem? Is Model 1, we still have to pay for factories, but we don't get to decide where they are. They're stuck wherever they are. Maybe we have a legacy network and we have factories wherever they are, they need to be there. We only get to determine the warehouses locations, and then the customers and the suppliers are fixed in both models. In Model 2, I get to determine both the factories and the warehouses. And our goal, again, is to minimize the fixed cost of operating factories, warehouses, and the variable cost of shipping and producing things at a factory to a warehouse. So those are the two models. Then the question asks, which of the following is true? And I would like you to pause here, think about this, and then come back and push play. So the correct answer here is A. Model 1's objective function value will always be greater than or equal to Model 2's objective function value. Let's unpack that. Okay, so first of all, we are minimizing cost. So what is good? Small is good. Okay, so if I read this, I can read this again that says Model 1's objective function will always be worse or the same to Model 2's objective function value. Okay. All right, so now let's think about that. So why is Model 1's objective function value always the same or worse than Model 2? Is that we can think about Model 2 has more flexibility. We have the ability to move both factories and distribution centers, which could lead to a lower cost solution, which is good. In Model 1, we don't have the ability to change the location of factories. Therefore, that could be in a less than optimal location, which has higher cost. You may say, okay, Model 1 did a great job of locating factories. That would be exactly where I'd locate them in Model 2. Then we would have equal, right? So we kind of got lucky in terms of the factory locations. Those are optimal in Model 2, then the solutions would be the same. So A is the correct answer. The reason that this comes in is that the more we have options to make decisions, that's always good in terms of potential for a better solution. So anytime we relax that something goes from an input parameter to a decision variable, if everything else stays the same, that always has the potential to either have the same performance or better. And the key thing is potential. However, what the challenge of that is, as we'll see in the next slides, is this makes it much more complicated usually to model, to think about. The combinations of different options increase greatly. And getting a solution to a model that's really, really complicated and then explaining it to decision makers is more challenging in model 2. And so from a optimization math, we can have the potential to get less cost, a better solution when we relax the fact that something is given and make it into a decision variable we get to decide. Flexibility is always good for that, but it makes it more complicated. So in recap, the correct answer is A. All right, so let's now dig into that. So if we want to actually formulate a multi-echelon capacitated facility location model, and in this example, we're gonna locate both factories and warehouses simultaneously. So we're gonna build one optimization model that says, I get to change the location of both factories and warehouses at the same time. And then the idea here is that we have supplies and we have customers. And so we have a given set of supply sources. So the supply is known. We don't get to change what our supply sources are. And we don't get to change the specified capacities coming out of those supply sources. So the blue is fixed. That's an input parameter. And then we also have the pink customers are fixed. So we have a set of customers that are known, they're given, they're an input parameter, and they have specified known demands. So what we do get to determine is the product flow from a supplier to the factories, from the factories to the warehouses, and the warehouses to the customer. So we get to determine that product flow. That's the quantity shipped and produced from one to the other. And we also get to determine where should I locate factories and where should I locate warehouses. And our goal is to minimize cost. All right, so let's do this mathematically. So in terms of something to think about is the multi-echelon capacitated facility location problem has similarities to just the single echelon capacitated facility location model, but it gets more complicated. So just out of the gate sets, we used to have 2 sets, now we have 4 sets, right? So we have set of factory locations, set of demand, set of suppliers, and set of warehouses. So those are our 4 echelons in the visual graphic on the previous slide. And so we have that, again, a set is just a collection of things. And then the input parameters you see have grown exponentially a lot. And so if you look at these in more detail, we basically need an input parameter for every single box, triangle, circle on that graph on the previous slide. So we need to know the number of markets, the number of potential factory locations, the number of suppliers, the number of potential warehouse locations. We also need to know the annual demand. That's similar to the single echelon problem. The potential capacity of each of the factories, again, similar to the previous one. But then what we have is we need this same information for warehouses. And then we have these costs of shipping, which we had CIJ in the last one. Well, now we have 3 places. We need to know the shipping from a source to a factory, from a factory to a warehouse, and from a warehouse to a customer. Again, input parameters are just pieces of data, so you just have a more complicated data set. So that's not inherently bad, but it is a lot more information. All right, and then in terms of decision variables and objective functions, when we have multi-echelon, we basically get to determine 2 types of facility locations and 3 types of flows. And so if you think about the facility location, that's again a binary decision variable. 1, if I locate a factory at site I, 0 otherwise, and 1, if I locate a warehouse at site E, 0 otherwise. So again, a facility decision is a 0 or 1 binary variable, but we have 2 types of those. That's why we have kind of 2 types of decision variables. And then we again use X to represent the quantity shipped, but now we need to consider all 3 of these parts of the supply chain. So from I'll start on the bottom, from the supplier to the factory, from the factory to the warehouse, from the warehouse to the market. All right, so those are decision variables. That's what we get to decide. And again, we want to change those such that we minimize the total cost of both the location, the facilities, and the transportation cost. And so how do you do that? This is our objective function. Again, this is really just adding together that you have all of these different aspects of the echelon. So this first FIYI is the fixed cost of factories. This FEYE is the fixed cost of warehouses. And then this is the cost from going from the supplier to the factory, and then how much do I ship between each of them? So that's the amount on the arcs. this is going from factory to warehouse, and then this is going from warehouse to the demand market. And so if you remember on a single echelon, we basically had one of these fixed charge and one of these variable. Now we have the whole thing represented. All right, and then the last thing is the constraints. And the constraints are where it gets a little bit more complicated. And I'll just display them all here, and then we'll talk through a couple of them. And so if you look at this first constraint, this should be somewhat familiar. And so what we're doing is we're summing over I, and we're saying we only have so much capacity at each supplier H. So this is basically saying out of each supplier, I can only ship what the most I have, and it goes then to factories. And so this is a capacity constraint, saying I only have so much supply at each of the suppliers, and then they get shipped to a factory. So you see that here. You will also see, if I skip down to this equation here, the third one, you have a similar thing going on, but now all of a sudden on the right-hand side, you have this yi. That's because we are determining factory locations. And so this is saying we only have so much capacity at each factory, but we get to determine where they are. So this is that fixed charge capacity constraint. So I only have capacity if yi is 1, if I decide to build the factory there. If I don't, that's 0, and this goes away. And so that's similar to the single echelon one, but now we have basically one here, and then on the right-hand side, the top equation, this is for warehouses. And so these are the same type of thing, but again, we get to decide where a warehouse is, and we only have capacity W of E if we actually build there. And so those constraints, the first one, the third one, and then the top one on the right-hand side are all, similar, but now we need more of them. Okay. The other thing that you've seen before is this demand equation. So on the right-hand side, we have demand of customers, and we need to meet that demand. And so what you're really looking at is just the last echelon from the warehouses to the demand. We need to meet all the demand requirements. And then the very last constraint you've also seen before, except there's now 2 of them, is that we can either build or we can't build. The only thing that makes sense is the 0 or 1. We can't have 0.6, 0.5, doesn't make sense in how we define our decision variables. So these are things you've seen before. There's more of them because you have multiple echelons of decision making, but hopefully those make sense. So there's 2 kind of constraints that are remaining, and that's this second constraint and this fourth constraint. And so what does this constraint say? It's saying we're summing up from the source, the suppliers, minus summing up into the factories has to be greater than or equal to 0. And so what does this say? Well, you could think about moving this to the other side, and basically what you're saying is what comes in can't be what has to be more or equal to what goes out. Okay, so what is going on here is what I'm shipping into a factory minus what I ship out of a factory has to be a positive number or 0. So this is basically saying you can't just have stuff show up at a factory that didn't get shipped to that factory and then ship it out later, okay? And that's similar what's going on with this equation here, the bottom fourth one. Only it's saying at a coming from a factory to a warehouse, what's getting shipped out of the warehouse had to arrive there. And these are sometimes called balance equations, so you can't just have stuff appear out of nowhere. All right, so here's kind of another test your knowledge about this optimization problem. Okay, so consider a network design problem where the goal again is to minimize the cost of producing products at factories, as well as the cost associated with transport between factories and distribution centers and transport between distribution centers and retail locations. Okay. Model 1 considers the location of factories as fixed, so we don't get to determine them, they're given, and determines which distribution center locations to open. So we do get to determine the location of distribution centers. Model 2, on the other hand, gets to decide both, the location of factories and the location of decision variables. My question for you is, which of the following is true? Again, I would encourage you to pause this video, think through it, and then push go. So the correct answer to this problem is A. A feasible solution to model 1 will always be an optimal solution. Or sorry, the correct answer is C. Sorry, A is not the correct answer. The correct answer is C. A feasible solution to model 1 will always be a feasible solution to model 2. All right, so let's unpack that. First of all, what is a feasible solution? A feasible solution means all constraints are satisfied, but it does not mean it's the minimum cost. And so if I look at model 1, which we basically say we have factories, and we determine where we should locate distribution centers, and we make sure demand is satisfied, we make sure capacity constraints are satisfied. This is feasible to model 2 because we've determined those facility locations, but it's not necessarily optimal. So the correct answer is C, that we have a feasible solution to model 1 will also be a feasible solution to model 2, but it's not necessarily optimal. And why is that? Because model 2, you could say, I can do better if you let me relax where those factories are located, and I change those, and so then I can actually get a better solution or a smaller cost solution. So that's why it's feasible, but not optimal. So correct answer is C. All right, and so one thing to note is I presented that because that is an adjustment to kind of the traditional capacitated facility location model. You can think of all kinds of other adjustments that could be made to these optimization models. One you could think about is, what if we counted for taxes, tariffs, or customer requirements? So in the things I just presented in this lecture F2, we were minimizing costs. That isn't always the right answer. You may think about maximizing some profit or revenue. And so we can modify that. And we may say we don't always need to meet all demand. What if we're not able to meet all demand? And so what we're doing is we're meeting as much a demand that exists, but not necessarily all of it. And then maximizing over the profits of what's going on. And so remember, profits is basically revenue minus cost. And so we're changing that from a min to a max. This is just one example of many things you could think about adjusting and making either more complicated or different. Just as kind of a side, is like I have a PhD student right now thinking about how to make a facility location model, considering that you have different types of facilities. So if you want to think about warehouses, you could build your own warehouse, you could lease using a 3PL, third-party logistics provider, or you could use on-demand warehousing, which is basically Airbnb for warehousing. And these are usually used in combination. And so his optimization models are considering all of these different types of facilities in one model. And so that requires, again, adjustments to these facility location problems, but they're things you guys are capable of doing. You just have to think about how to logically do that. So hopefully that helps, and I would encourage you as you go into the world to realize that we can adjust these models for consideration and thoughts at very specific businesses or scenarios.